In modern statistics, the raw material is noise. Analysts often face datasets containing millions of entries, chaotic collections of survey responses or medical trials, where individual outliers can easily be mistaken for a meaningful trend. When humans look at this volume of clutter, our pattern recognition tends to find a signal in what is actually just random fluctuation. To navigate this, statisticians rely on the hypothesis test. This procedure provides a rigid framework to determine if an observation is a genuine breakthrough or simply a mathematical coincidence. At its core, a hypothesis test acts as a rigid binary filter. It takes a messy sample of data and runs it through a set of parameters, forcing the researcher to quantify their exact level of confidence before making a final determination. Every statistical result retains a margin of error. By calculating that specific probability, the test allows an analyst to move past subjective guesses and arrive at a single mathematically supported decision. Every statistical decision hinges on the relationship between two numbers. The first is the level of significance, denoted by the Greek letter alpha. Alpha represents a researcher's preconceived risk tolerance. It is the maximum allowable probability of making a specific statistical error. By rule, this threshold must be locked in strictly before any data is collected. If a specific level is not given for a study, the scientific standard is an alpha of 0.05, representing a 5% risk tolerance. The second half of the equation is the p-value. Unlike alpha, which is predetermined, the p-value is calculated directly from the observed sample data. The p-value answers a highly specific question. What is the exact probability of obtaining this specific sample data under the strict assumption that the status quo is true? Alpha is the line drawn in the sand. The p-value is the footprint showing where the actual sample data landed relative to that line. The entire mechanism of a hypothesis test boils down to a single geometric comparison, seeing which side of the alpha threshold the p-value falls on. To see how this geometry works, we start with the null hypothesis, or H0. This is the mathematical assumption of the status quo. By definition, it always contains a symbol with an equal sign. Opposing it is the alternative hypothesis, or HA. This represents the specific change or effect a researcher is looking for, and its mathematical structure dictates the physical geometry of the test. The mathematical inequality you use in the alternative hypothesis determines the physical shape of the probability curve you are about to analyze. A less than parameter means a left-tailed test, pushing the probability entirely left. A greater than claim runs a right-tailed test, shifting the area right. Asking if a parameter is simply different requires a two-tailed test, dividing the region symmetrically into both extremes. The phrasing of a research claim translates directly into physical geometry. It tells the analyst exactly where on the curve the p-value needs to be calculated. Let's apply this. Suppose an 8-year-old swimmer averages a time of 16.43 seconds. His coach wants to know if a new aerodynamic pair of goggles improves his speed. We establish our known baseline population variables. The mean time is 16.43 seconds, and the population standard deviation is known to be exactly 0.8 seconds. This chart displays a standard normal distribution. Because we have the rare advantage of knowing the true population standard deviation, we use this normal curve, setting up what is called a z-test. The center peak represents our null hypothesis, a mean of 16.43. The alternative hypothesis claims the goggles make the swimmer faster. In racing, faster means the time will be strictly less than 16.43 seconds. Because of the less than claim, we run a left-tailed test. The swimmer takes 15 practice runs, dropping the sample mean to 16.0 seconds. We calculate the area to the left of this new value. This isolated section is our p-value, calculating to exactly 0.0187. This means if the goggles did absolutely nothing, there's only a 1.87% probability of averaging 16 seconds or less. We check this against our predetermined alpha level, using the standard 5% threshold. The sample p-value is physically smaller than the alpha risk tolerance. The data is too rare to be dismissed as random chance. Following the mechanism, we reject the null hypothesis. That model relies on having perfect baseline data. But in practical research, analysts rarely know the exact standard deviation of an entire population. Imagine a statistics instructor who suspects the true average score on an exam is higher than 65, but they only have access to a tiny sample of 10 student scores. Without the population standard deviation, the parameters of the standard normal curve break down. It can no longer be used accurately. This graph illustrates the necessary workaround, the student's t-distribution. When missing the population data, analysts must substitute the sample standard deviation and warp the underlying geometry to compensate. The squashed peak and fatter tails physically map the increased uncertainty of a small sample. With the new geometry set, the test runs normally. A sample mean of 67 and a right-tailed test land the new p-value at 0.0396. Once again, we compare this result to our 0.05 alpha threshold. Even though the probability model had to adapt to accommodate missing information, the final step remains identical. The p-value is less than alpha, so the null hypothesis is rejected. Rejecting a null hypothesis provides strong mathematical evidence, but it does not prove the alternative is true with 100% certainty. Because hypothesis testing relies on isolated samples, there is always a quantifiable risk that a sample has randomly misrepresented the broader population. This matrix shows the 4 possible outcomes of any test, contrasting the actual physical truth of the universe against the analyst's mathematical decision. When you reject a null hypothesis that is actually true, you commit a type 1 error. This is a false positive. Your alpha value is the exact parameter that sets the maximum acceptable limit for making this specific mistake. Conversely, failing to reject a null hypothesis that is actually false results in a type 2 error, a false negative. The entire architecture of a hypothesis trust is an exercise in risk management, optimized to balance the danger between these two inevitable errors. Ultimately, quantitative research relies on one universal mechanical rule. If the p-value is less than or equal to alpha, you reject the null hypothesis. If the p-value is greater than alpha, the data is not statistically significant, the evidence is insufficient, and the null hypothesis survives. Your parameters might change, and your distribution curves might shift from z-tests to t-tests based on the data you have. But this geometric comparison is constant. The hypothesis test empowers analysts to navigate the vast space between pure ignorance and absolute certainty, providing a rigorous mathematical compass to map the noise of the real world.